Hello viewers, welcome to this module on multiple linear regression model or the classical linear regression model. In this module, we will introduce the concept of the multiple linear regression model and we will discuss the basic features of the model. In other words, we will lay down the assumptions of the model and finally, we will take an intuitive look at how to develop a working rule to estimate the parameters of the model. So, in order to make things simple, we begin with a 3 variable model, which is the simplest form of the multiple linear regression model or classical linear regression model. The model in 3 variable form is written as y I is equal to beta 1 plus beta 2 x 2 I plus beta 3 x 3 I. Now, first some terminology. So, x 2 and x 3 are the variables which explain y and y is the variable which is explained. So, this is called the explained variable, whereas x 2 and x 3 are called the explanatory variables, or they are known as the regressors, whereas y is known as the regressand. But this expression, as we have written it, is an exact expression or a deterministic expression. Let us understand the difference between a deterministic expression and a stochastic expression. So, we introduce the random disturbance term ui and that now becomes a properly specified stochastic expression for y. So, yi depends on x 2 I, x 3 I plus a random disturbance. This is called a random disturbance term. It is called a random disturbance term. Now, why do we need to extend the 2 variable model? We can have very simple examples. For example, production would depend on labor inputs and non-labor inputs, which we are just writing as machines. So, output or production depends on labor input and non-labor input. Another simple example, earnings of an individual would depend on not only the years of schooling, but also vocational aptitude. So, once again, the explained variable y is dependent on 2 explanatory variables x 2 and x 3. One could be years of schooling, the other could be vocational aptitude. We will now go further and deeper into the model. Now, let us look at the classical nature of the model. Why do we call it a classical model? Let us look at the assumptions that make the model a classical model. The first assumption is that expectation of ui is nil, which means that in the population the average of all these random disturbances is nil. So, they cancel out. So, that on the average the random disturbance term has 0 effect. Secondly, we have variance of ui is equal to sigma squared. As we have seen, the observations run from 1 to n, but the variance of each of these ui's is the same. So, this is known as homoscedasticity. The technical term is homoscedasticity, which is equal variance. So, each of the disturbance terms has equal variance. Thirdly, the covariance between two disturbance terms is 0. So, between any two disturbance terms there is no association. This is also known as absence of serial correlation or non-auto correlation. So, this is no auto correlation. And then we also say that this disturbance term follows a normal distribution. So, we say that ui follows a normal distribution, and you can see that the mean is 0 and the variance is sigma squared. So, each of the ui's follows an identical and independent normal distribution. So, it is written as independent normal. That means ui and uj are independent. These are the 4 basic assumptions of the classical model. Next, there are some ancillaries, such as we say that the model does not has any specification error. What is the meaning of this? We had given 2 examples. One was the example of earnings on the one hand and the 2 explanatory variables, years of schooling and the vocational aptitude on the other hand. So, if this is the model, we are assuming that this is the correctly specified model. So, to say there are no major variables which are omitted from the model. And in the k variable model, we will have beta 1, beta 2 up to beta k, and so the number of observations has to be greater than the number of parameters to be estimated. So, we say number of observations n should be greater than the number of parameters k. K is the general format where you have yi beta 1, beta 2 x 2 up to beta k x k. Further, we say that variance of each of the explanatory variables is not equal to 0. In this case, variance of x k, these are not equal to 0. That means, for each variable that we are using as a regressor, each of the explanatory variables will have values which are not constants. It will have a variance, it is not equal to 0. And covariance between the disturbance term and any regressor is also equal to 0. So, there is no association between these random disturbance terms and this regressor. This is fundamental, because otherwise we would not have written beta 1 plus beta 2 x 2 plus beta 3 x 3 plus u. So, u contains this variable u, random variable contains any other effect apart from the x variable. So, there is no association between these two. Finally, we have linearity in the parameters. We will explain, we will take some time to explain this, and no perfect multi-collinearity. No perfect multi-collinearity. So, these are the basic assumptions, but I repeat 1, 2, 3 and 4, these are fundamental, the others are ancillary. Moreover, this holds because we will be using cross section data, and in cross section data the x variables are non-stochastic, they are non-stochastic. That means, when we write y I equal to beta 1 plus beta 2 x 2 I plus beta 3 x 3 I plus u I, the stochasticity of y arises from the stochasticity of u. So, the x variables are non-stochastic, that automatically satisfies this condition. Let us now take a closer look at the concept of linearity. So, what exactly do we mean by saying that the model is linear? Let us demonstrate. We know that the relation between output and cost is non-linear. So, this equation that shows the relation between cost of production and output would be given as C I equal to alpha 1 plus alpha 2 Q I plus alpha 3 Q I square plus alpha 4 Q I to the power 3 plus U I. That means, this cost equation is non-linear in the Q I's. Of course, this is very clear, it is a non-linear relationship, but the multiple linear regression model is so powerful, it can capture this kind of a relationship through the feature of linearity in parameters. Let us see how. So, we can represent this as yi is equal to beta 1 plus beta 2 x 2I plus beta 3 x 3I plus beta 4 x 4I plus ui. So, that means these alpha parameters are now shown as beta parameters. We could have also written alpha, would not have made any difference, but the important point is Qi has become x2i and Qi square has become another variable x3i, Qi cube has become third variable x4i. So, that retains the character of linearity. It is not linear in the x's or not linear in the Qi's, it is linear in beta 1, beta 2, beta 3 and beta 4. The model is linear in the parameters, not linear in the variables. This is very important. And it is also important to be able to represent the 4 basic assumptions in matrix form. So, we had said expectation of ui is equal to 0, which means we have u1, u2 right up to un, expectation of that is equal to 0. Similarly, variance of u is sigma square, sigma square, sigma square again sigma square, and these off diagonal terms are all 0. Let us try and understand what these off diagonal terms are. So, this is called, this u is this vector. So, this is called the variance covariance matrix, and this is written as sigma square I. It is written as sigma square I, and that means all the diagonal elements, each of the diagonal elements shows the variances. This is variance of u1, variance of u2, right up to variance of un. And remember, we had said that the covariance between any two ui uj, I not equal to j, that covariance is equal to 0. So, all the off diagonal terms, they show the covariance. So, in matrix notation, we write this variance u, instead of saying ui, we write u, because u contains the entire vector, and covariance are the off diagonal terms. So, these are two very important things, that is, we have to be able to express these two conditions, expectation ui equal to 0, that we write as expectation of u is equal to 0, and variance covariance conditions we write as variance of u is equal to sigma square I. Let us now take a look at the full k variable model represented in matrix form. The explained variable, as we know, is y, and there are n observations. A matrix is nothing but an array of entities, that means we arrange them in a particular order, which makes it easier to handle, and each of these y's we know are explained by the x variables. So, we write x1, x2 through xk, because y1 is explained with the help of x1 through xk. Similarly, y2 is also explained with the help of x1, x2 through xk, and finally yn also explained with the help of x1, x2 through xk. But this being the first observation, we will also have to put in the subscript 1. So, for the first observation of y, the explanatory variables are first variable x1, first observation, second variable x2, first observation, through kth variable xk, first observation, and similarly for all the others. And each of these need to be multiplied by the corresponding betas. So, we now write beta 1, beta 2 right up to beta k, and the nth y variable is associated with x1, nth observation, x2, nth observation through xk, nth observation. So, that if we now put in the square brackets showing the matrix, that is basically our k variable model, and plus of course, we have the disturbance terms ui, u1, u2 up to un. So, that is the matrix formulation of the k variable model. Once again, it is written as y is equal to x beta plus u. This is the u vector we have already introduced, u1 to un. This x matrix has order k columns and n rows. That means it is of order n cross k. This is k cross 1, this is n cross 1, and therefore, this is also n cross 1. Now, we will move on to the estimation part of this model, and needless to say, before going for the k variable model, we will develop a working rule for the estimation of the 3 variable model, which is the simplest form of the multiple linear regression model. To do that, first we write yi equal to beta 1 plus beta 2 x 2 I plus beta 3 x 3 I plus u I. This is an example. So, here k is 3 x 1, x 2, x 3, and this beta 1 we do not see any x over here, which means this x 1 is equal to 1. So, x 1 1 is equal to 1, x 1 2 is equal to 1, this is x 2 2, this is k 2. So, the first column is basically a unit vector which takes care of this intercept term. The x variable associated with beta is 1 because beta 1 is an intercept. So, the other x variables are regular x variables. Now, this model, when we estimate this model, we write it with a hat. So, y hat is beta 1 hat plus beta 2 hat x 2 plus beta 3 hat x 3, and we cannot estimate the random disturbance error. So, how do we actually estimate beta 1 hat, beta 2 hat and beta 3 hat? We start from this equation and we will say how to develop a working rule for getting beta 1 hat, beta 2 hat and beta 3 hat. We write summation y and we sum. So, we get n times beta 1 hat plus beta 2 hat summation x 2 I plus beta 3 hat summation x 3 I running from 1 to n, I running from 1 to n. That is why you have n, and here you have I going from 1 to n. So, the working rule is, first jot down the estimated equation, then instead of putting y hat we put y over here and we sum all this. So, that is called the first equation. Secondly, what we do is we multiply y by the second variable. So, we have y I x 2 I summation equal to beta 1 hat summation x 2 I plus beta 2 hat summation x 2 I square plus beta 3 hat summation x 3 I x 2 I. Everywhere I runs from 1 to n, I runs from 1 to n. So, starting from the basic estimated equation or the idea of the estimated equation, we have to get 3 conditions in order to get these 3 beta 1 hat, beta 2 hat, beta 3 hat. How do we get these 3? First, sum the equation, second, multiply with x 2, and by now viewers have already guessed that the third one will be multiplying y I with x 3 I and I going from 1 to n. So, the first one will be beta 1 hat summation x 3 I, second one will be beta 2 hat x 2 I x 3 I, and the third one will be beta 3 hat summation x 3 I square. So, now these equations are called normal equations. Now, what is the idea? Why are we doing this? Because actually viewers, you might have noted that here we had put y hat, but when we go to these conditions I am not putting y hat. The reason is the actual y is this estimated y plus the error of estimation. Actual y is estimated y plus error of estimation. So, saying that this is equal to this means the error is equal to 0. So, this first one means summation error E I is equal to 0. So, the average error of estimation is 0. What does the second one mean? It again means that the error E I is not correlated with xi. What we are doing is y minus the first part on the right hand side, and then we are multiplying by x2. So, that means we are multiplying E with x2. That means summation EI xi is equal to 0. This is the sample counterpart of the population property, expectation or covariance between ui and xj is equal to 0. So, here also error does not depend on x2, and finally, this would mean that summation EI x3i is equal to 0. Summation EI x3i is equal to 0. So, the three simple conditions, total error or average error is equal to 0, error must be uncorrelated with the second explanatory variable, and error must be uncorrelated with the third explanatory variable. Needless to say that readers are anticipating that if we have k variables, then this will go up to summation EI x ki I running from 1 to n, that would also be 0. So, in that case, how many equations do we have? From 2 to k, and then the first one. So, we have from 2 to k makes k minus 1 equations, and this is 1. So, we have k equations for estimating beta 1 through beta k. So, that now gives us an idea about how to estimate the variables beta by using observations. This module therefore has explained three things. First, the introduction and the rationale for the model. Second, how we characterize the model, what are the basic properties of the model, what are the classical features, and finally, an intuitive understanding of how the model is estimated.